Hi all, welcome to new class. Today's class is about the mathematical models of control systems. The input-output relations of various physical components of a system are governed by differential equations. So, the mathematical model of a control system constitutes a set of differential equations. So, the mathematical model of a control system constitutes a set of differential equations. The response or output of the system can be studied by solving the differential equations for various input conditions. So, by using the equations, we can find the behavior of a system. So, there are two ways to find the behavior of a system, that is theoretical and practical way. So in theoretical representation there are again two different ways. One is input output representation, that is again divided into two. Input output representation means input and output differential equations, that is in time domain. So in this manner, in this method, we use the input output differential equations in time domain. The second one is transfer function representation, and that is in frequency domain. And another method is state model. State model, that is input output states in time domain. So these are the theoretical approach for finding the behavior of a system. And in practical method, that means applying the input, we get a corresponding output. So here we apply an input and we get a corresponding output. Such an approach is known as system identification. So in this method, the graph should match with the model graph. Next is time invariant and time variant system. So if the coefficients of the differential equations governing the system are functions of time, that is coefficients of the differential equations are functions of time, then it is called time variant function or time varying. And if the coefficients of the differential equations governing the system are not the function of time, then it is called time invariant. Example for time invariant function are transfer function, and examples for time variant functions are state model. Linear and non-linear systems. So a system is said to be linear if it obeys superposition principle. So if it didn't obey this superposition principle, it is called a nonlinear system. So what is superposition principle? The superposition principle implies that if a system model has responses y1 of t and y2 of t to any inputs x1 of t and x2 of t, so these are the output and these are the inputs, then the system responds to the linear combination of these inputs a1 x1 of t plus a2 x2 of t is given by linear combination of the individual outputs a1 y1 of t plus a2 y2 of t, where a1 and a2 are constants. The principle of superposition can be explained diagrammatically as shown. So let H be a linear system. So this is the input, x1 of t and x2 of t are the input and y1 of t and y2 of t are the outputs. So this is the linear combination of the inputs with the constant a1 and a2, that is x1 of t here x2 of t. So this is the linear combination of the inputs. So here we get a1 x1 of t plus a2 x2 of t. So this is the linear system. Then this is output y3 of t, and for linearity this y3 of t should be equal to a1 y1 of t plus a2 y2 of t. So this is the superposition principle for linearity. And a mathematical model will be linear if the differential equations describing the system has constant coefficients. Next is transfer function of the system. The differential equations of a linear time invariant system. Linear time invariant system. So what is linear time invariant system? If the coefficient of the differential equation describing the system are constants, then the model is called linear time invariant. So the differential equations of a linear time invariant system can be reshaped into different form for the convenience of analysis. So one such model for single input and single output system analysis is transfer function. So the transfer function of a system is defined as the ratio of Laplace transform of output to the Laplace transform of input with zero initial conditions. So Laplace transform is obtained by converting the time domain into S domain. So transfer function is the Laplace ratio of the Laplace transform of output to the Laplace transform of the input with zero initial conditions. So what is Laplace transform? So here the time domain is converted into S domain, that is the Laplace transform of the function f of t is equal to f of s. So this is the function in time domain and this is in s domain. So Laplace transform of function f of t is equal to f of s, and that is equal to integral 0 to infinity e to the minus st or e raised to minus st f of t dt. So this is the Laplace transform of function f of t, that is integral 0 to infinity e raised to minus st f of t dt. So this f of t is the function in time domain. Let us study about the Laplace transform of some functions. First one is the Laplace transform of e raised to at. So the Laplace transform of e raised to at is integral 0 to infinity e raised to minus st into e raised to at dt. That is equal to integral 0 to infinity. This one we can write e raised to a minus s t dt. And what is the integral of e raised to x, or integral of e raised to x dx is e raised to x plus c. So here we can write e raised to a minus s, and this is a constant, so here we have to divide with a minus s to the limit 0 to infinity. And we can take this 1 minus 1 divided by a minus s outside. So here e raised to a minus s to the limit 0 to infinity, and that is equal to 1 by a minus s e raised to infinity minus e raised to 0. So what is e raised to infinity? So here we have to put s greater than a. So here we get 1 by a minus s. So here there is t here, 1 by a minus s into e raised to minus s minus a into t, because we have to consider s is greater than a. So to the limit 0 to infinity, otherwise we will get infinity as the answer. So here 1 by a minus s into e raised to minus infinity. So this is wrong one. So e raised to minus infinity minus e raised to 0. So put the values 0 and infinity to the t. And here 1 by a minus s into e raised to minus infinity is 0. Then minus e raised to 0 is 1. So we get minus 1 by a minus s, that is 1 by s minus a. So the Laplace transform of e raised to at is 1 by s minus a. And here if we put a equal to 0, we get a Laplace transform of 1, and that is equal to 1 by s minus 0, that is 1 by s. And two important theorems in Laplace transform are initial value theorem and final value theorem. Initial value theorem is limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s. And final value theorem is limit t tends to infinity f of t is equal to limit s tends to 0 s into Laplace transform of f of t, and that is equal to limit s tends to 0 s into Laplace transform of f of t is nothing but f of s. So these are initial value theorem and final value theorem. So transfer function equal to y of s divided by r of s. Let y of s be the Laplace transform of the output and r of s be the Laplace transform of the input with zero initial conditions. So this is about the mathematical models of control systems. Thank you for watching the class. If you like the classes, please like, share and subscribe my channel.